The next factor, the next factor is the factor which can contribute to surface defect is the metal flow pattern, which result from the gate design. This flow pattern is established during the gating and the gate design process for the part, and there are some design rules that have been established for designing gating and gate, and they should be followed, which I suppose. And when we are designing, we also design die design and manufacturing die design nowadays. So we follow the guidelines which is given by this NADCA. So, and the some things we also validate with the time of experience. Okay, it's the practice of using a grinder to modify the gate for a part should never be used. This process is not precise enough to ensure that the resulting gate complies with the design rule. All right. So yeah, there's some video also you can find out how to calculate the gate area as per this casting volume. All right. So design rules are valid, and the best chance of success it is follow this rule. The important point is that there are be drawing for the gate design, and that there be some justification for the decision that were we made. So this is also again we can help the PQ square analysis, and this should always include the PQ square calculation, right? In order to familiarize you with the gating and the gate design rules, there are some summarized on the next two slide. As mentioned previous, the gate design process through is another. We take some other classes or some webinars on that. In that we will discuss the in detail this gate design, right? Okay, so now we summarize this uh, design rules. All right. So the PQ squared process has been developed to determine the approach. I just would like to give some brief about this PQ square, because we are using many times this PQ square, PQ square, PQ square. So PQ square just an analysis in which we check the compatibility between the machine and the die. So we draw there some machine line with respect to this gate velocity. All right, and this the diagram or this PQ square analysis between pressure and the flow rate. Pressure and the flow rate. For example, what flow rate we require to fill this casting, we calculate. What maximum flow rate can machine produce, we calculate. So we compile this calculation with the help of this PQ square analysis. Through that, we find out the this gate and gate area and the plunger size. Okay, so just I just give the brief. What is PQ square? PQ square. All right. So the PQ square process has been developed to determine the appropriate process parameter for a part, and this process permit the machine, the die, and the casting process to be matched for each other. You can say all the parameter like casting pressure and the machine tonnage and plunger diameter, gate area. So all the four or five parameter we can compile together with the help of this PQ square. All right, the casting is divided into fill zone, as I earlier told you. If you have a variation in your volume in your casting, so you divide in the several section with respect to their volume, and according to that we will find out the filling time, and then we will find the gate area. All right, so the gate are appropriate so that the each zone is filled in the same amount of the time. So some of the designer what they do, they find out the gate area with the help of this calculation and divide it in the equal ratio. But this should not be happen. It's divided with respect to the volume of sections we have divided in the casting. It is being to gate the part so that the metal flow is the short way across the casting, right? It is the best to gate the part so that the metal flow is the short way across the casting. We try to avoid mixing the metal flow different gate unless it happens very close to the gate. We can use vector. If some of the guy you study some simple vector lines, so you put your casting physically or in 3D model also and locate your gate area and just draw a vector line throughout the casting, and you can see where the metal flow will intersect in the casting without any simulation or other things. Just put your casting shot, or you can say shot, on a paper, A3 size paper, and draw your gate angle, right? And remove the casting or shot and just draw a vector line throughout the casting. So you will find where the all gate line will intersect in the casting. So you can easily understand and memorize or visualize where will metal intersect and where it can be create some turbulence and where it can be air in turbulence entrapped in a casting. So it should not be happen. So the gate angle and number of you can say gate number you can decide by just drawing these vector lines. So this is a this thing happens when we don't have this such technology like simulations. So we would do these things, and I'm also doing sometime because all the time I don't use this simulation technology. Okay, so it is best to gate the part so that the metal flow is the short way across the casting. We try to avoid mixing the metal flow from different gate unless it happens very close to the gate. We also want to get gate into heavy section, right? And this is the important thing. Yeah, we also want to get into heavy section to minimize porosity. What kind of porosity? Shrinkage porosity. Very specific. If you give the direct gate in a heavy wall thickness section, it will help to minimize your shrinkage porosity or to meet a surface finish requirement in certain area of the part. Okay, now we have another slide. When designing gate, the designer will avoid jet flow velocity and try to distribute the metal flow as much as possible. Put the gate in a location where venting can be provided on the opposite side of the casting from the gate. Right, this is the important thing when you are putting some number of gate. So you have also identified there's some place in opposite to give the air venting. It is best to avoid having metal impinge directly, of course. We have to avoid direct gating in a core, but this is sometimes unavoidable. Yes, this is the sometimes unavoidable. So what we can do to minimize some jet flow, we have to use some more gate area so that we can reduce the gate velocity, and which will help to reduce the turbulence and the jet flow that particular area in front of cores, right? One key in a runner design is to keep the runner length equal. Yes, if you have a number of runner or more than one runner in your casting, so keep equal length. Runner should not look like a branches on a tree. The transition should be very gradual and smooth. Yes, I always try to use a round runner. But many in on many shop floor you will see the uh, square or rectangular kind of runner. But always use round runner, and it is very easy to uh, decrease gradually towards the gate area, and it will also help to maintain heat from gate area towards to screw boost, so that you will avoid shrinkage porosity or flow porosity, or you also minimize the air interruption, because the greatest shape to flow any fluid, it's circular shape. So when you are designing a round runner, right, it will help to reduce your air intrusion. Okay, so when designing gate, it is important to prevent eddies. As the metal flow, these eddies will result in casting defect. We want gate designing so that the molten metal has a high momentum as it fills the die cavity. So this is the yes, I think yes, this is these are the guidelines we can keep in mind when we are designing gate and the runner. Okay, to for a good metal flow. Okay, so we discussed the normal fill time for various alloy previously. On this slide, the minimum and the maximum gate velocity for aluminum, zinc, and we have also for magnesium. Okay, so let's talk about the aluminum only. The minimum velocity is based on achieving atomized flow and could be lower for the part with very thick gates. The maximum is based upon the erosion and the soldering are likely to occur, and this can have depend on the shape of the part. In some situation, yes, in some situation, higher gate velocity could be appropriate. Yes, so the below maximum there is a much less problem with the gate erosion, but the minimum should be watched, and the casting made below the minimum velocity just don't work. You can see the aluminum is 100 inch per second, and maximum is 1600 inch per second, or you can say which I used in my design. So preferably 35 to uh, 50 meter per second, 35 to 50 meter per second gate velocity. We are talking about the gate velocity. Why 35 and why 55? There's some logic uh, to assuming or taking this gate velocity, because we need some casting pressure, because we are casting high pressure die casting. We are not casting gravity casting or low pressure casting or other casting. If we are casting in a high pressure die casting, so some casting pressure. If we are talking high pressure die casting. So what we are talking about? High casting pressure. High casting pressure. We are not talking about the high machine pressure. No, if you see all of the mostly tonnage of machine, if you are taking 120 ton to 3000 ton machine, so you will get the mm, same machine pressure, or you can say pump pressure, like 150 to 160 kg per centimeter square. But when we are talking about high pressure die casting, so we are talking about the casting pressure, high casting pressure die casting, you can say. So we need some casting pressure, minimum casting pressure. So if you know about this, so minimum casting pressure we use 600 to you can say 1000 kg per centimeter square, some range as per casting application. We are casting like only aesthetic part required 600 to 700 kg per centimeter square. On the other hand, engineering or leakage proof part required 800 to 900 kg per centimeter square. So according to that, we need minimum gate velocity. right? And there's some formula through which we can calculate this minimum or maximum gate velocity. So yes, in this slide, this formula is not available, right? So the formula is P. Yes, you can write down if you interested to know how we identify the minimum and the maximum gate velocity. The formula is P is equal to CT multiplied by VG square, which is driven from the PQ square calculations, right? Which is driven from the PQ square calculation. The formula is again, yes, speaking. P is equal to CT multiply VG square. If you put P like 700 and the CT value is a point 0.5 for aluminium, so you will get the your VG, which is gate velocity. All right.